Estimating earthquake magnitude from Sentinel-1 satellite imagery is crucial for effective disaster response and mitigation. Traditional seismic stations are resource-intensive, limiting global coverage. Machine learning models offer a lower-cost solution by monitoring Earth observation data. However, accurate magnitude estimation is a low data regime problem due to limited historically recorded earthquakes. To address this, the authors propose a novel metric learning approach, training models to estimate earthquake magnitude from Sentinel-1 satellite imagery while ranking pairwise samples. This approach has shown a significant 30% improvement in mean absolute error (MA) over prior regression-only based methods, particularly transformer-based architectures. The proposed method has the potential to provide more accurate and timely earthquake magnitude estimation, enabling effective disaster response and mitigation. By leveraging the increasing accessibility of Earth observation data, this approach offers a promising alternative for monitoring seismic activity and estimating earthquake magnitude. The significance of this research lies in its potential to improve global coverage and reduce costs associated with traditional seismic stations. By developing machine learning models that can accurately estimate earthquake magnitude from satellite imagery, the authors aim to contribute to more effective disaster management and mitigation strategies. The QuakeSat dataset is introduced, comprising Sentinel-1 satellite imagery samples varied by earthquake magnitude, with each sample consisting of a pair of pre- and post-earthquake event images with two bands, VV and VH. Visualized as false color images, these samples are accompanied by their corresponding magnitudes. The application of satellite imagery for earthquake magnitude estimation holds promise, but it is hindered by the limited availability of historical earthquake data combined with satellite data, resulting in a low data regime problem. This challenge can limit the performance of regression models. To address this limitation, a novel approach is proposed, reformulating earthquake magnitude estimation as a metric learning problem. This approach trains models to not only predict earthquake magnitudes from Sentinel-1 satellite imagery but also to rank pairwise samples based on their relative magnitudes. This dual-objective training enhances the model's ability to generalize from limited data, improving its accuracy and robustness. The proposed approach makes two key contributions. Firstly, earthquake magnitude estimation is formulated as a metric learning problem, incorporating both regression and ranking objectives to facilitate learning. Secondly, this solution is applied to several state-of-the-art convolutional and transformer-based models, resulting in a significant improvement in mean absolute error (MA) of over 30%. Synthetic aperture radar (SAR) imagery has revolutionized Earth observation, providing high-resolution images under all weather conditions. Advances in SAR imaging techniques have significantly enhanced data quality and applicability in fields such as topographic mapping, ground deformation detection, agriculture, and hazard management. In seismology, there is a growing interest in leveraging machine learning and deep learning techniques for real-time earthquake detection, distinguishing between earthquakes and microtremors, and phase picking. Approaches include the use of convolutional neural networks, generative adversarial networks, and transformers directly on seismic wave data. However, Sentinel-1 imagery has traditionally relied on manual analysis for earthquake analysis. Recent research has introduced the QuakeSat dataset, which utilizes bitemporal Sentinel-1 imagery for earthquake detection, demonstrating the potential for automated solutions with SAR imagery. The magnitude estimation task can be formulated as a regression problem, where a machine learning model is trained to predict the ground truth magnitude value given a set of time series images related to the same spatial area at different time steps. The model is trained using a margin ranking loss function, which encourages the model to distinguish between high magnitude samples and lower magnitude ones. The margin ranking loss is expressed as LMR, x1, x2, y, equals max 0, y, x1 by 2, plus m, where y is defined as 1 if x1i greater than equals x2i and 1 if x1i less than x2i. This approach enables the development of automated systems for earthquake analysis, leveraging the strengths of SAR imagery and machine learning techniques. The authors introduce a novel loss function, L, which combines mean squared error loss, LMSE, and margin ranking loss, LMR, to estimate earthquake magnitudes from Sentinel-1 imagery. The margin ranking loss, LMR, is defined as the maximum margin between predicted magnitudes from two sets of images, S1 and S2, with a margin m. The final loss function, L, is a sum of LMSE and LMR. In the experimental setup, a mixture of convolutional and transformer-based models, including Convenext v2, MobileNet, MobileVit v2, and VitNI, are trained to investigate the effect of model size on earthquake magnitude estimation. The models are trained on the QuakeSet dataset using the Torch Geo implementation, with a batch size of 16 and 10 epochs. The AtomW optimizer is used with a linear learning rate scheduler and a peak learning rate of 1e4. The models are initialized with ImageNet pre-trained weights, and the input images are pre-processed by converting to decibels and applying random horizontal and vertical flip augmentations. The results show that the proposed approach is effective in improving the performance of all models, both convolutional neural networks, CNNs, and vision transformers, VITs. The Convenext model achieves the best results overall, particularly when trained with the margin ranking loss, followed by the VIT model. The MobileVit model, which combines convolutional and transformer-based architectures, provides good results with lower computational resources than the VIT model. The MobileNet small model achieves a competitive performance with the lowest computational resources, while the MobileNet large model tends to overfit and performs poorly. The comparison of models trained with the margin ranking loss and those trained only with the mean squared error loss reveals the contribution of the additional term in improving the performance of the models. The results are evaluated using the mean absolute error, MAE, between the estimated and ground truth magnitudes, as well as the flops computed on an Intel Core i9-10980Xe CPU. Estimating earthquake magnitude in Sentinel-1 Imagery via ranking. A novel approach to estimating earthquake magnitude from Sentinel-1 Imagery is presented, reformulating the task as a ranking problem. This method leverages existing magnitude labels, eliminating the need for additional data, and exploits the rankings between predictions within a batch to increase the distance between samples with different magnitudes. Experiments on the QuakeSet dataset demonstrate the efficacy of this approach, with results presented in Table 1. Various architectures, including Convenext, MobileNet, MobileVit, and VIT, are compared with and without the margin ranking loss. The addition of the margin ranking objective significantly improves performance across all architectures, as measured by the LMR-MAE metric. The best performing model, VIT, achieves a LMR-MAE of 0.2613 with the margin ranking loss, outperforming baseline models. This suggests that the ranking-based approach can effectively capture the relationships between earthquake magnitudes and Sentinel-1 imagery features. The advantages of this method include its ability to utilize existing data and its potential for real-world applications in earthquake monitoring and response. This approach offers a promising solution for accurate earthquake magnitude estimation, leveraging Sentinel-1 imagery and ranking-based formulations. However, you didn't provide the transcript content that requires refining. Please share the text so that I can help create a direct, concise version for a voiceover narration summary, targeting an audience of expert researchers and stakeholders within a technical domain, ideally in a range of 250,000–350 words.